Another interesting aspect of orogenic wedges is the way in which they interact with surface processes that erode the surface of the wedge or sculpt it into a mountain belt. The orogenic wedges have a very specific kinematic pattern of deformation, and that deformation, including uplift, will then drive a very specific pattern of topography, which will then interact with surface processes and erosion. And in this podcast of this interaction. So for example, what you're looking at here is a numerical model. That's coupling deformation and surface erosional processes. This is an orogenic wedge. This cross-sectional cutout shows the deformation with a zone of thrusting in each direction. It's uplifting the central region, forming a doubly divergent wedge. As it uplifts and it moves to the left because of the subduction process, you don't see the slab, but the subduction is coming in from the right and then diving down and going underneath the plate on the left. So this is the pro wedge and this is the retro wedge. This is uplifted and it's carried then in the direction of the overriding plate. And as it goes, it's eroded. This is done again through numerical processes, but there is surface erosion occurring on this on here, sculpting these mountains with the valleys and rivers and so on. And it's that interaction then that I'd like to look at in this talk. So here's a little schematic cartoon of an orogenic wedge. Again, we have doubly divergent wedge. It's being driven by subduction down here. We have pro wedge here, retro wedge here. We have then a pattern of crustal thickening and shortening across the overall system, uplift of the center and formation of a wedge that's tapering in this direction and this direction. Now this whole system is driven by accretion of new material into the orogenic wedge system. And by accretion, I mean really the off-scraping of either sediments or crustal layers. This could be crustal naps, any kind of material that's scraped off of the downgoing plate and added into the orogenic wedge. This represents then a mass flux, right? This is and in fact, the flux is equal to the velocity of the material coming in times the thickness here. That gives us the units of flux. But this represents then mass that's being added to the system, where the system is defined to be this orogenic wedge. Now, in the real world, once this is up above sea level, there's a second mass flux term, and that's the erosional mass flux. So once it's above sea level, material will be eroded by whatever surface processes we might have, rivers, hill slopes, landslides, glaciers. All of these processes are going to act on the surface to remove material and carry it down into the forelands or eventually out of the system. This is also a mass flux, right? So this is, units don't matter, but it represents material being removed from the system, where the system again is defined as the orogenic wedge. And we can think of two cases: a case where where these fluxes, well, depending on what the magnitude of these fluxes are, there are two cases. There is the case where the accretionary mass flux is larger than the surface mass flux. That's what's being indicated in this upper figure. If this condition is met, that means that the orogenic wedge must grow with time. More material is added than is being removed. It's going to grow with time. And this is what we refer to then as a constructive state of the orogen. It's one in which the orogenic belt is being constructed. It's growing because of this positive mass balance. In this case, we have all the conditions that we saw in some of the earlier talks with, like in the sandbox experiments. We have thrusts that are forming in both directions as the deformation propagates outward. So if we refer to this as a deformational front, which is the leading thrust going outward from the mountain belt, this is a kind of deformational front. This will be propagating in both directions away from the mountain belt with time as this grows. Now we can contrast this to then the second case, which is where the surface mass flux is larger than the accretionary mass flux. All right, so that means the erosion is removing more mass than is being added in by accretion. And this is what we'd refer to then as a destructive orogen. In this case, then the orogenic belt needs to be getting smaller with time. Now that means that in particular, if we look at the retro wedge and the retro wedge front, that means that if the wedge is getting smaller, this deformational front would be abandoned and the active deformation would jump into the interior of the mountain belt. So this is indicated here as the front is retreating away from this active mountain belt. Why? If the wedge is getting smaller, if the mass balance is negative, the wedge has to get smaller. It has to maintain its shape by critical wedge principles. That means that it will maintain that self-similar form, but at a smaller size. So it's shrinking. And if the taper angles remain constant, but the mass is shrinking, that means that this front will have to retreat. Now, one could say the same thing is true on the pro wedge front. This it may well be that this front is also retreating back inward as the wedge is getting smaller, but this is not so clear because all of the new material that's coming into the wedge is coming in at this front. That's in fact why the pro wedge is different from the retro wedge. The accretionary flux is coming from this side. And that means that new material is being constantly pushed into the wedge from this side. And that new material being added means that the new material has to be thrusted and deformed. And it could be that this thrust front continues to advance outward, right? Because it has to deform in order to accrete new material. So in fact, this destructive orogenic system is sort of indeterminate in its prediction for what happens to the deformation front on the pro wedge side. So does this happen? Yes, we think we can see this sort of thing happening. Incidentally, I should mention there is a third state between the destructive and constructive origins, right? What if the two are equal? That's what we refer to as a steady state origin. And it will sit right here in the middle then between constructive and destructive. And the mass fluxes would be equal, the size would not change, deformation would continue, but the size would not change with time. So let's look at an example. How do we see this sort of thing? And importantly, how do we recognize this sort of thing in, say, the structure and tectonics of a mountain belt? All right, so here's our usual cross section, or one of our usual cross sections of the Alps. This is a doubly vergent orogenic wedge formed by subduction of the European crust underneath the African or Adriatic plate over here, right? So pro wedge is on the north and the retro wedge is on the back. And the question is, how has the size of this wedge changed with time, and how does that reflect both the accretionary processes, but also the erosional processes? Now, clearly, every mountain belt has a history of growth in its early stages. If it starts from nothing, it's going to grow out of nothing. That's going to be a constructive phase. As it gets bigger, it rises above sea level, erosion starts, we start to remove mass from the surface. As the mountain belt gets larger and larger, as we continue this process, that erosional flux is going to get larger and larger as well. Right? It must, because the mountain belt is getting bigger. For in a constructive state, it'll get bigger. That means more surface area. More surface area is subjected to erosion. The mountains are higher. Higher mountains have higher relief. Higher relief means faster erosion. So this is a good example of a system with a negative feedback. The bigger the mountains are, the larger the erosional flux, the slower the rate of growth. And this is why this is a system that we would think at least has a tendency to move towards a steady state, where the accretionary flux would be balanced by the erosional flux. So those are the sorts of things we're looking at. I'm going to step back one more time and say, okay, if we think a mountain belt starts constructive but ends towards a steady state, maybe it could go into a destructive state. We'll talk about the reasons why, but it might bounce back and forth between constructive and destructive. How do we recognize that in geology? And I would argue that one of the key ways to recognize this is to ask what's happening to the retrodeformational front, okay? If it's in constructive state, that means that this front must be propagating outward away from the mountain belt. If it's in a destructive state, it must be moving inward. And if it's at a steady state, it should be constant, fixed in space, right? So that's kind of key. Whereas if you look at the pro-wedge front, it's very hard to say whether it's growing or not because you have this constant accretion of new material. That means constant deformation. And trying to estimate the size of the wedge, the width, and so on is very difficult because we don't really have a fixed reference point. Everything is deforming all the time. And so it's very difficult to say reconstruct exactly, say, what the deforming width of the Alps were back in the Miocene or the Oligocene, something like that. But it's not really necessary in that we can just rather carefully focus our attention on what's going on, say, back here at the retrodeformation front. So let's do that. Let's look back here. Okay, so first of all, what was the early history of the Alps? Well, the early history of the Alps was in fact backthrusting along, say, the Insubric line. This is where the highest pressure rocks are exhumed. So we had the maximum backthrusting going on here early in the history. As the mountain belt got larger through the Oligocene into the Miocene, we started to have more and more increasing deformation of the southern Alps, that is the extent, the region to the south of the Insubric line, right? This should represent a constructive phase of the mountain belt then. If it's expanding in this direction, it's in a constructive state because that's the retrodeformational front. In fact, the southernmost thrusts of the Alps are found under the Po Plain sediments. The Alps reached their maximum extent sometime in the late Miocene with thrusting all the way back here. And I can show you that in map form here. So this is a map of, here's the Alpine region. You can recognize the Lake Como, Maggiore is here, Garda is here. So this is kind of the main Alpine front. Here's Milano. Right along here, we go down to all the way across Italy into the Ligurian Sea down here. So this is the Po Plain over here and the Apennines coming through here. So Milan and this, and if we look at some seismic cross sections, I'm going to show you a couple of sections across here, What you can see is that underneath the Po Plain, all right, so here's the topography, dead flat, zero, barely any, there's no topography in the Po Plain at all, right? But if you look in the underground, what you see is through seismic data, this is seismic reflection, interpreted seismic reflection data, you see a series of thrust faults down here at depth, right? These are, in fact, deforming middle Miocene sediments. So that means that the thrusts were propagating into the foreland after the middle Miocene. And by the time you get to the end of the Miocene, which is the Messinian stage, it's hard to tell if they were still active, but there's sediments ponded behind, so that could be either paleotopography on these, or it could be that they were still active in the Messinian. But by the Pliocene, there's no deformation. And these sediments up here are Pliocene. This, in fact, is a classic interpretation of the interaction between the tectonics, the deformation, and sedimentation, in that these sediments are deformed, these sediments are not. That tells you when these faults shut off. And they shut off about the start of the Pliocene. Okay, so, and clearly they're not active today. And there is no topography out here. This is just full of sediment. That's why the Po Plain is so flat. So how would we interpret that? This is then, we would interpret this as an abandoned deformational front. So it was something like this, where the deformation had reached a point south of Milan in the case of the Alps. This structure was abandoned. It went inactive. Deformation jumped back into the interior of the Alps, where it's harder to recognize because it's in the metamorphic rocks now, and at least in the Pliocene, it was deforming in the interior. But these structures out here were abandoned. And what that means is that we've shifted from either a steady or a constructive state into a destructive state. And this would have happened then right at the end of the Miocene, start of the Pliocene. So I'm going to go back a couple slides and look at this again, just to remind you where we're looking. We're looking out here. So these structures were active through the Miocene, and then they were abandoned. Deformation jumped back out here where there's topography. This whole region was then filled in with sediments and covered because these thrusts were not actively uplifting anything anymore. So this is a transition between constructive to destructive state of the Alps at the start of the Miocene. So why did that happen? Well, and I'm going to go back again to this one and say, all right, why do we go between constructive and destructive states? The mass balance must have changed. And here we have two possibilities. We switched to a case where the accretionary mass was larger than the erosional mass flux, and then we switched to the case where the erosional mass flux was larger than the accretionary mass flux. Why would that happen? Well, there's two possibilities. Either the accretion got smaller or the erosion got larger, right? All we know is that the ratio between the two changed. How do we tell? Well, there's different ways we can tell. One of the ways is by looking at how much sediment was coming off of the Alps in this time period. This is the total eroded sediment, at least it's an estimate. This is a very difficult thing to estimate, but this is an estimate of the total eroded sediment that came off of the Alps over the last 30 million years. And what you can see then is that there was, with some changes, there was actually pretty close to constant amount of sediment coming off until about 5 million years ago, at which point the erosion or the eroded sediment increased. So thinking back to our problem of a moment ago, if we went from a constructive to a destructive origin at 5 million years ago, start of the Pliocene, at the same time that the sediment flux was increasing, that suggests that in fact it was the erosional flux that increased, not the accretionary flux that decreased, right? Why would the erosional flux increase? Well, that could be a climate effect, for example. This is getting the time at which the Northern Hemisphere was cooling. First glaciers were appearing, at least in the last few million years, maybe back this far, oh, that's a little bit far. But the climate was changing. If that changing climate then increased the erosional flux from the Alps, that would drive it from this constructive to destructive case. All right. Well, I want to sort of switch topics now and talk about a different way in which climate and erosion interacts with orogenic wedges, and that's in the spatial distribution of erosion. So climate does interact with the tectonic processes. If we build a mountain belt by orogenic wedge processes, the climate operates, depending on the climate, the surface processes operate. We have erosional processes. Again, this is, all our rivers, glaciers, whatever. But there is an interesting effect that we think we can see in this interaction between the processes. And that is what's sometimes called the rain shadow effect, or orographic enhancement of precipitation, in that the weather always seems to come from one direction. Depending on where your mountain belt is relative to the oceans and the jet stream, depending on which hemisphere you're in, the dominant wind directions, or it's what's really a moisture flow direction, we have this interaction between this incoming storms that tend to rain out as they encounter the mountains, and then have a drier side, or a rain shadow side, where the rainfall will be very heavy on this side and very dry on this side. And this can actually lead to some detectable differences in the structure and tectonics of a mountain belt. So I'm going to give you a couple of examples which serve to illustrate how this happens. I'm going to start with New Zealand. New Zealand is the South Island of New Zealand, which is a small orogenic belt. It's actually dominated by strike slip faulting. This is the Alpine fault that is a plate boundary between the Australian plate and the Pacific plate. But it's not a pure strike slip fault. It has a small component of convergence across this. And that convergence has, in fact, led to the formation of the Southern Alps of New Zealand, which are a pretty good sized mountain belt. Still small orogenic belt, but it's sort of alpine in scale, maybe a little bit smaller. But these are real mountains. They're highly deformed. If I look at the structure, oops, I'm going to have to pause for a second and fix my screen. Sorry. Okay, so if we look at the structure of New Zealand, the Southern Alps, what we see is that in fact this convergence across the Alpine fault has led to the formation of an orogenic wedge. There's a root to the crust. There's a detachment that's lie underneath the pro wedge of the system, and it probably connects up then with the Alpine fault to bring material up here. So we've got a kind of a doubly vergent wedge structure here, pro-wedge, retro-wedge. We can look at the deformation. We can look at the thrusting associated with the alpine fault or the other thrusts that are here. The whole zone is pretty widely deformed. But the other thing that's interesting about New Zealand is the climate, in particular what the spatial distribution of the rainfall is. This is the average annual rainfall across New Zealand. And down here in the southern island, we have an incredibly strong gradient. So the blue zones down here are mean annual rainfall of up to over 6 meters, right? So this is heavy, heavy rain, right? But on the other side, on the eastern side of the mountains, it's actually kind of like Zurich sort of numbers, sort of normal 800 millimeters, this sort of level of rainfall. So we've got a very strong gradient. And this is, again, this rain shadow effect. The moisture is coming in off the Tasman Sea from the west. It hits the mountains and boom, it rains out everything, right? By the time it gets over, then it's not really doing very much. And so if we look at the combination of the tectonics and the erosion, we can sort of see this impact. In particular, if we look at things like the thermochronometric ages. So this is the age versus distance from the alpine fault, which is here. So we're looking at a cross section across the Southern Alps here. This is looking at zircon and apatite ages, both fission track and uranium, thorium, helium ages. And what you can see is that the ages are very, very young right here, right? This zone here is very young ages. They're hard to read here, although the axis is going up several 100 million years. The point being that everything back in here is largely unreset. These are inherited ages that are old because they're really set back in a different orogenic system. Whereas these are young and are reset along the front here. Why? Well, this is probably reflecting the erosion and the exhumation that's occurring in the region right next to the alpine fault. So because we have heavy rainfall, we have heavy erosion, we're bringing up the rocks relatively quickly against the fault. And we're seeing this in terms of the young ages for this 10 or 20 kilometers that are right up next to the retro deformational front. So if we try to sort of summarize that with sort of a cartoon pattern, how is it that this wind shadow effect, rain shadow effect is being manifested in here? This is the Southern Alps of New Zealand. This is just a kind of an idealized cross section of the elevation, which is here. The total exhumation, which is represented by all those young ages, it's maximum right here. And the rainfall, precipitation, which is also maximum on this side and falls off quickly like that. So we have this correspondence then between the rainfall, the exhumation, and kind of an asymmetry in the elevation. Although I'm going to argue in a minute that we don't know actually what's cause and effect here. But this is the pattern we see then in the Southern Alps. So I want to contrast that with the second example now. And that's an example that I'm going to take from the Northwest United States, North America, right at the Canadian-US border, in fact, up in the Olympic Mountains. So this is an oceanic subduction zone. This is the Cascadia subduction zone here. We have a slab coming underneath the coast of North America. And this is in fact forming a big accretionary wedge. It's the classic marine accretionary wedge. The top of that wedge has now emerged above sea level and makes up this coastal mountain range that comes along here from the Klamaths Coast Ranges, the Olympic Mountains, which I'm going to look at here, and Vancouver Island. So this is a coastal mountain range where we have active erosion occurring today. So this is kind of the structure and the cross section coming across here. It looks like this. If we zoom in on the Olympic Peninsula, this area here, what you can see is that you can see a kind of a metamorphic core that's been exhumed in the middle of the Olympics. These are kind of low-grade metamorphic rocks that are now have been brought to the surface by erosional processes. But this is material that was once accreted into the accretionary wedge, and now it's come up to the surface and sort of ringed by what's really kind of almost an ophiolitic basalt sequence or terrain that kind of rims this, where the erosion is considerably less. So there's the climate effect here, as in New Zealand. There's another one of these rain shadow effects. We can see that again in the average precipitation here. This is in inches, which is good for you to learn how to use, I guess. But this is not millimeters, but inches. But so multiply by something like 10, right? 12 inches is 30 centimeters. But the point here is that this is very wet along the coastal region. This again is going up now to 180 inches, which is several meters of rainfall annually that's occurring on the seaward side of the mountain range here. And the backside then is relatively dry. In fact, you can see the how much rain there is by just looking at the ecosystem out here. This is the west coast of Washington State in the Olympic Mountains, where this is in fact a prime example of a temperate rainforest. That's just the moss growing on the trees there. It tells you get quite a bit of rain here during the year. All right, well, we can see again in the evidence for erosion that goes along with that heavy rainfall. We see that in exhumation and thermochronometric ages. So this is a map view of ages. These are now fission track ages from either apatite and zircons. So they're either indicated as pairs or, well, that's all you need to know, or single ages, but the number in the middle then is the age, but that's probably easiest to read over here on the right, which is showing now a cross section with these ages projected in onto the section. So this is from the coast here going across the central metamorphic core region, AA prime here, for example, that's going along here. And what we see here is that unlike New Zealand, the ages closest to the coast are in fact not very young. The youngest ages are found in here, okay, sub 10 million year ages, for example. These are found in the core of the mountain belt in here. In fact, they're a little bit older out here, and they're older as you move out into this direction. So here it's not really mimicking the rainfall one-to-one, but rather has more of an integrative pattern. And to really understand that, you have to think a little bit about the kinematic paths that the rocks are taking as they're accreted into the front of the wedge and then coming out the top. All right, and that's maybe best shown, well, you can look at any of these, but this is a wedge. So here's the wedge, here's the upper surface. Material is added either into the front or it can be added into the base of the wedge through what's sometimes referred to as an underplating process. This is referring to things like nap stacking on very low angle detachments, right? That would, or low angle thrust faults, that would add material to the bottom of the accretionary wedge from off of the downgoing oceanic plate. So that can happen too, or it's added into the front or it's added into the base through some kind of structural underplating mechanism. But in any case, it then is deformed inside the wedge, and then material will come up to the surface. So we end up with a kind of a flow pattern, material coming in and coming up to the top. It comes to the top through erosional processes. So here where we have high erosion rates, this is in fact the anerosion rate function. It's maximum along the coastal area and moving inland, but then has this rain shadow effect, so it's lower erosion rate back here. Now we can take this kind of a kinematic pattern and predict what the thermochronometric ages would be at the surface based on this pattern. And the prediction is that, in fact, the kind of odd ages here, but the prediction here is that the frontal part of the system, so this is the coast right here, the coastal area would have relatively old ages. And the reason for this is because these rocks have not been buried deeply enough to reset the thermochronometer. All right, so remember our thermochronometry lecture, what these ages are really telling us. An age, thermochronometric age, is the time it takes to get from a closure temperature deep in the earth to the surface. So if there's a closure depth of like 10 kilometers, that's what this red line is representing, then if it's at 10 kilometers, then the age of the surface here, like 18 MA, reflects the time it takes to get from 10 kilometers up to the surface, 18 million years. All right. On the other hand, the rocks that are out here by the coast never got below that temperature. right? If you look, these lines are the path that the rock takes from accretion up to the surface. And anything out here actually never was down beneath this 10-kilometer isotherm in order to have its age set back to 0. So this pattern of age that we see at the surface has a big zone where there's simply just not enough exhumation, but we don't know what the erosion rate was. It may have actually been very high in this area. We simply don't know because the ages can't measure the transition because they never crossed this closure isotherm. On the other hand, from here back to here, we can then measure the time that it takes to come from 10 kilometers up to the surface. So this pattern, I'm going to step back again. This pattern is in fact reflecting the kinematics that are happening inside the wedge. Out here, unreset. Here, the highest erosion rates, the youngest ages. Back here, lower erosion rates. Why? Because we're moving into this rain shadow. There's less rain back here, less erosion, lower erosion rates. The ages are getting a little older again. Okay. So again, to summarize then the pattern for the Olympics in kind of cartoon fashion, the elevation, the topography looks something like this in the Olympics. Exhumation, erosion is maximum in the middle of the mountain belt because it's right here where the heavy rainfall is interacting with the mountains, right? So the precipitation looks like this, heavy rain out along the coastal area, but in fact the exhumation is maximum back here in the interior. And in fact, if we contrast those two, then we see that we can have this contrast between New Zealand and the Olympics. So here again are what we have is now these are now oriented so that the wind direction, the precipitation is from the same direction. But in fact, what we have is a case where the subduction is going opposite to the wind in New Zealand, and the subduction is going in the same direction as the wind under the Olympics. And the result is that the exhumation patterns look very different. The topography, in fact, is, well, you tell me, what's dominating the topography here? Because you're not here, you can't tell me, but the topography is being dominated by the subduction process. It's steepest on the retro wedge, and it's less steep on the pro wedge. So we have this asymmetry that's being driven by the wedge tectonics. The rainfall is driving the exhumation, and so we have the heaviest erosion rates on this side and on this side. So in one case, it's the pro wedge. The other case, it's on this case, it's on the pro wedge. This case, it's on the retro wedge. Because the pro wedge is carrying material through the mountain belt, the exhumation ends up being maximum somewhere in the interior of the mountain belt. In New Zealand, the exhumation is maximum right at the edge of the mountain belt. So you can see if we can recognize, say, in an old mountain belt what the pattern of exhumation is, we might be able to use that to say something about what the structures are, what the polarity of subduction was, and maybe even something about what the polarity of the rain shadow and the local climate was. Okay, thank you.